Alright, welcome back. We are picking up with our descent through calculus curve sketching with the shape of the graph. Like I mentioned in previous videos, up until this point in time, you've been able to sketch extremely rough versions of the graphs of different functions, but within calculus we try to get a little bit more precise, talking about specific values for the maximum, minimum, x-intercepts, y-intercepts, and behavior. Some values, obviously, some components or aspects that you learned in previous math courses. This one is definitely new. So when we talk about concavity as it pertains to the shape of a graph, we're talking about the way the graph bends. Okay? So we have a couple different pieces here of how graphs may behave, and what is concavity's relationship to tangent lines. So if I were to draw in some tangent lines here, we can see that we have a negative tangent line to a horizontal tangent line to a positive tangent line. And if I were to draw in some tangent lines here, right? Let's say this has a slope of 1, we can see that our tangent lines start to get steeper and steeper and steeper. Right, so we have this behavior where the slope, I shouldn't use that, slope of tangent is increasing, which obviously would be the different effect here where we have positive to horizontal to negative. But what happens here for this, right? Because the overall behavior of the function is going downwards, but take a look at the tangent lines, right? So we have a very steep slope currently, let's say -6, and the slope of that tangent line now is -4, and -2, -1, so on and so forth. So the negative value continues to increase, -6 to -4, right? -2, so the slope of the tangent line is still increasing, whereas that is not the case here, right? We can see steep tangent line that broadens out over time. So when that happens, right, when the slopes of the tangent lines are increasing, we say that the function along that interval is concave up. And yes, your intuition is correct. If the slope of the tangent line is decreasing, we would say that the function along that interval is concave down. Oops. But let's define concavity officially so we can all be on the same page. And let's say let f of x be a differentiable function on an open interval AB, then f is concave up on AB if f prime of x is increasing on AB. And this kind of makes sense, right? The slopes of the tangent lines are increasing, so if the function behavior of the derivative is increasing, it correlates. And vice versa. F is concave down on AB if f prime of x is decreasing on AB. Now, and I had made reference to it in our initial example. But I will redraw this piece a little more magnified. Let me draw the tangent lines in a different color. Right, so we can see that we're going from steep to more broad in our slopes of the tangent line. So, just to reiterate, it is possible to have a function that is decreasing, right? Because this function, like a roller coaster, is going downwards, while its derivative increases in this graph. The slopes of the tangent lines are becoming less steep, and in turn less negative. Okay, so just to echo one more time, just because the function itself is decreasing does not mean that we ought to assume that the concavity is downwards. And obviously vice versa. If the function is increasing, we can't just auto assume that the concavity is concave upwards. So, we just defined concavity utilizing the first derivative. However, we can also test for concavity using the second derivative. So assume that f double prime of x exists for all x in AB if the second derivative is greater than 0, aka positive, for all x in AB, then f is concave up, and vice versa. If f double prime of x is less than 0 for all x in AB, then f is concave down. But how do we determine whether or not f double prime of x is greater than 0, f double prime of x is less than 0? Well, it all depends on a point. So we define a point C, f of C is a point of inflection if the concavity changes from up to down or down to up. But we can't just, the way we did with the first derivative, assume that any of those values where the first derivative is undefined or where it's equal to 0 are critical points, right? We don't say that, oh, these are all inflection points. So let's define a test for those as well. Alright, test for inflection points. The good thing is it's very similar to finding critical points. So once again, we've got to assume that the second derivative exists if f double prime of c is equal to 0, and f double prime of x changes sign and x equals c, then f of x has a point of inflection at x equals c. If it doesn't change sign, or if it's not equal to 0, well, no point of inflection. We're going to pause there though, and we're going to pick up with part 2 of this video segment, where we delve into some practice. See you there.